View exponential growth and decay. So if you remember what the function looks like for exponential growth or decay, we're going to write y equals a times b to the x. A is your starting value, your initial value. So a is your start. It's kind of like the y-intercept. B is your rate of growth or decay. So this will be your growth or decay. And then x is typically the amount of time that has gone by. All right, so that's what an exponential function looks like, and we're going to use that to solve the warm-up. You are examining a petri dish containing 5 of a certain type of bacteria. The bacteria triples every hour. Can you write the function? All right, well, our starting value is 5. If it triples every hour, it's to the third power, and then x would be the amount of time that has gone by. How many bacteria would you have in 4 hours? All right, so we can plug in for time here. So we have 5 times 3 to the 4th power. I downloaded the Desmo scientific calculator, so if you don't have one, this one works pretty well. And so we're going to type in 5 times 3, and then to get to the power of it's that A with the little B button next to the A squared button. And there it is. So 5 times 3 to the 4th power is 405. So we'll type that in. So after 4 hours, there is 405 bacteria now on that petri dish because they keep tripling every hour. About how long will it take until there are 10,000 bacteria? So this time we have the 10,000, the number of bacteria, and we want to know what it equals or what time will give us those 10,000. So now we're solving for x. So right now we don't have an algebraic way to solve for x, so what we've been using is guess and check. And we can just guess and check it as is. We can do 5 times 3 to a power and try to get 10,000. I like to make the number smaller, so I am going to get rid of the 5 on the right-hand side by dividing by 5 first. So we'll get 2,000 equals 3 to the x power. And now I can guess and check with this. I can do 3 to a power and try to get 2,000. So I'm going to pop up again my scientific calculator. And again, it's 3 to what power? And I know it's more than 4 because at 4 hours it was 405 bacteria, so I'll go to 5. And again, the number I'm looking for is 2,000, and that's too small. So let's try 6. Okay, that's bigger. Let's try 7. And you can see at 7, I hit that 2,000 mark. I'm a little bit over. So I know it's going to be a little bit under 7. So I'll do like 6.9. That's pretty close. I'll keep going. 6.92. Ooh, that's pretty close. Look, it's 2002. So I'll go a little bit lower. 1. I need go a little bit higher. So how about 1.5? A little bit too low at 1.6. 7, 8. These are getting closer. Oh, and that's pretty close, right? That's the 2,000. So I'm going to say about 6.919 hours. All right, so let's write that down. So by guess and check, we figured out that if x is about 6.919 hours, then we get pretty close to the amount of bacteria that we're looking for. So this is time. All right, so yesterday we did practice doing these methods for solving, and we're going to review more of that today. So I did divide this into 2 different parts. One, just looking at the equation, telling growth or decay and starting value, and then part 2, we'll take a look again at the word problems. So in part 1, can you just give me the initial starting value? I'm going to call my starting value the A value. So what's the starting value? And then is it growth or decay? So if you take a look at the first problem, our starting value is 8. And then if we take a look at growth or decay, we have to look at this number. Is it bigger than 1 or less than 1? Less than 1 is decay, bigger than 1 is growth. So this is like $1 minus a quarter, which is 75 cents. And that's less than 1. So if we're taking 75% of something every time, it's getting smaller. So this is an example of decay. Let's take a look at the next one. 3 is the base right here. And that number is bigger than 1, so we're tripling something every hour, just like the bacteria in the petri dish. So this is going to be growth. All right, how do I know it's the base? It has the exponent next to it. So we're missing the starting value. If you don't see the starting value there, it's an invisible 1. So here our A value is 1. It starts at 1, and it triples every hour. All right, let's take a look at the next one. Here the A value, we can see it's 1900. And then if we take a look at the B value, the growth or decay rate, that's 1.5. This is bigger than 1. So it means you're going to be increasing or growing every hour. So this is growth because the 1.5 is bigger than 1. Let's take a look at a graph. The starting value is the y-intercept. And so here the y-intercept is at 4. So the A value is 4. And we can see this is growing. So this is growth. And E right here, the starting value is 2. And we can see this is decreasing as we go from left to right. It's going down. So that is decay. All right, now let's take a look at the word problems. Write a function that models each situation and solve the following questions. During normal breathing, about 12% of the air in the lungs is replaced after one breath. So 12% leaves your body, and there's still 88% left in your body. Write an exponential decay model for the amount of original air left in the lungs if the initial amount is 500. And then how much of the air is present, original air is present after 240 breaths. All right, so we'll start with our starting value. We're starting with 500 milliliters of air. It's decreasing 12% every breath, and X would stand for the number of breaths. So so this is 100% minus 12%. That's the same as 88%. So I'm just going to rewrite the function combining like terms. And what we're looking at here is we have 88% of the original amount of breath in our lungs after each breath. And so now we want to figure out after 240 breaths how much of the original air is left. So we're going to plug that in for X. So I'm going to type it in my calculator as this, 500 times 0.88 to the power of 240. And then let's see what I get. So I'll type it in here, 500 times 0.88 to the power of 240 breaths. And we get a very small amount left. In fact, here's what, I'll try to show it on this calculator. Let's see what happens. Oh, I have to clear this. So 500 parentheses 0.88 to the power of 240. And what you see is scientific notation. So 2.37 times 10 to the negative 11th means we move the decimal place over 11 times to the left. So that's a very small number. So I'm going to show you how small that is. So there's not much of that original breath left. I'm going to do it down here just because I'm running out of room. So here's what we saw. Okay, so what this means is move that decimal place over 11 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so I'll put a dot. I'll put zeros here. So we can see that very little, very, very little of the original breath is left after we take 240 breaths. Most of it has left our body. Okay, let's try the second example. I'm going to erase this. So this says the foundation of your house has 1,200 termites. The termites grow at a rate of 2.4% per day. How long until the number of termites doubles? All right, so here we're starting with 1,200 termites. It's increasing 2.4% per day. All right, so it's increasing 1 plus, and then I'm going to change the 2.4% to a decimal, so that's 0.024, and how you can get that is you can take 2.4 and divide by 100. So the 1 is going to make it increase, the 0.024 will make it increase at 2.4%, and we want to know how long until our population doubles. So if I double the 1,200, I get 2,400, and here's my equation. All right, so now we solve. Let's divide each side by 1,200 just to get rid of that number on that side. And we know that 2,400 divided by 1,200 is 2. I'm going to combine like terms here. The 1 plus the 0.024 is 1.024 to the x. And now I'm going to guess and check this. Again, when we don't know the exponent, we guess and check it. So when I type it into my calculator, I'm looking for how long until it doubles. And is this per day? Yeah, per day. So it's the number of days until it doubles. All right, so I'm going to pop up my calculator, and I'm going to clear this, and I'm going to do 1.024, and what the number I'm looking for is 2. So I'll just try, I don't know, 8. Nope, too small. Let's try 9. Too small. Let's try like 15 days. Again, I'm looking for when it doubles. Let's try 30 days. That's pretty close, right? So I'm going to say 30 days, and we get that number 2 there, which is what we wanted. So when X is about 30 days, so after a month, the population has doubled. All right, let's take a look at our last example, and then you'll be able to try this out. Okay, so you drink a beverage with 120 milligrams of caffeine, so like a cup of coffee. Each hour, the caffeine in your system decreases by 12%. How long until you have 10 milligrams of caffeine in your body? Okay, so this is a decay problem. Let's start with the starting value, 120 milligrams. It's decaying at 12%. So it's kind of like the breathing problem that we did. So to rewrite this, we could say y equals 120. 1 minus 0.12 is the same as 0.88 to the x. And we want to know how long until we have 10 milligrams left. All right, so again, a guess and check problem when we're solving for the exponent. Let's divide each side by 120 just to make the numbers easier. Okay, so I get about this I change colors here. So what we're looking for is 0.0833 repeating equals 0.88 to the x. All right, so again, we're going to guess and check this. I'm going to type this into my calculator. I'm going to look for this number, 0.0833 repeating, and figure out how many hours that takes. So let me pop this up. Okay, clear this. So it was 0.88. To what power gives us 0.083 repeating? So I'll just pick a number, 6. Too big. Clear. Oh, just delete that. How about 1? Okay, we know what 1's going to be. All right, 2, that's too big. 3, this is getting smaller. Let's try 15. Let's try 20. Ooh. Let's try, how about 18? That's pretty close, right? Because we want 0.0833, and that's 0.1. What if we go to 19? That's pretty close. So that's 0.088. So what happens here is this is what scientific notation. Okay. Oh yeah. Okay. I should put point. Oh, that's too small. Again, I'm looking for 0.083. Oh, that's pretty close. I'm trying to get back there. How did I get that? What if I did point? I want to make this 0.083. Oh, that's too small. Okay, this is pretty close. So 0.0826 I get. So about 19.5 hours. Okay, so let's pop back here. And we'll say, all right, when x is about 19.5 hours have gone by, that's almost the whole day, you only have the 10 milligrams left of caffeine in your body. All right, so your assignment today is to practice this, and some of the equations will be plug and chug, where you just plug into the equation, kind of like this one right here, and some will be where you have to guess and check it. So the answer key will be on Google Classroom, so you can check your answers.